Today we're getting some simple structural section properties from a parametric section. You can do I shapes, can do C shapes, and L shapes. And a reminder that you can get more tutorials like this at our website, and you can also download the scripts if you prefer rather than building them yourself from the videos. And feel free to have a look at some of the other services we offer, including model conversion, reinforcement, visualisations, etc. Alright, so we're going to start off with a few rectangles. And to specify them, I'm going to set up some sliders. I'm going to call this one width. I'm just going to copy that and call this one height. Then I'm going to set up a rectangle. And what we need for those is domains, so we can build them easily with this construct domain command. And I'm going to start it with 0 and go to our specified width, so say 200 mil. I'm going to do the same for the height. I'll make the height 132 mil. Put that into X, that into Y. That's a basic rectangle. Now, just to show that a bit more clearly, I'm just going to use this boundary surface, which just creates a surface out of boundary lines. So now I've got the red rectangle. Now if I want to build a complex section, the way I'm going to do it here is I'm going to just stack them on top of each other. You can create I's and C's, L shapes, angles pretty easily through this method. So I'm just going to turn that height down a bit. Now I want to create another rectangle, so the easiest way to do that is just copy and paste that. Now I'm gonna do a length, a leg of the L there, so I want it pretty thin and pretty high. But it needs to be moved slightly because we've got a bit of an overlap, you can see there. So I'm going to use a move command. And to move it, I need a vector. Now I want to move it up by the thickness of the previous section, which I know, I've called it height here, in the Y direction. So that's better. I'll just unpreview that so it's clear that we've got the two legs. Now what I'm going to do is, as I said, create a composite section of these. And there's a cool little command in Grasshopper that's really useful for this. It's in intersection. It's called region union. And it will take boundary curves and it will create a single region. So we've got two regions with boundary curves. I'm just going to hold down Shift. And you can see that's joined up all the lines and created a single region, which is exactly what we want. So if I unpreview the separate rectangles now, I use that for the boundary, for the surface. We've just got one single surface, which is what we want. Now I'm going to keep going. I'm going to put another top flange on here and make it into a C. I'm going to make the assumption that I'm going to use the same top and bottom flange. So I've already got that rectangle, but I just have to move it by a different amount. So I'm going to move that rectangle again. The amount I'm going to move it is the sum of the two heights that I've got. So in maths, I'm going to do a mass addition. I'm going to add the two heights into that. That total height I'll put into Y. If I preview it, yep, that's correct. So that's made our C. I'm going to add that to our union. Turn that off again. So there we've got a C. And we can obviously adjust the top and bottom flanges. We can adjust the height of the flanges as well, which is going to obviously change the total height of the section. All the variables easily controlled. And another little cool trick you can do in Grasshopper is you can double click on one of these lines and it creates a relay. So if I wanted to turn this back into an L easily, I just unenable it and I've got an L back. I can do that with this as well, so I can go back to the rectangle. Okay, so now it's pretty basic stuff and we want to get some section properties out of these shapes. So luckily Grasshopper has some pretty advanced functions. One of them is allows us to get properties straight out, and it's called it's under analysis in surface area moments. And it takes some geometry, which we've already got. I'm going to use the boundary. And you can see it's popped up a centroid of this section. So if, for example, I turn off that top flange, you can see the centroid is roughly 2/3 down the L section, which is exactly what you would expect. So what does that give us? It gives us the area of the section, the centroid, the inertia, a moment of inertia around the centroid, which in engineering terms we call the second moment of area. It's got some error on its calculation, which is very small. The second moment of inertia, which I'm not going to be using for this demo, and the radius of gyration, which is a useful property for engineers. So I'm just going to have a little text display next to the section so I can quickly see results from this component. So to do that, I'm going to start with the radius of gyration. I'm just going to round this up. Then I'm going to use the text display sorry, it's in display. This one here, 3D text tag. I'm going to put the nearest rounding up, so 143 millimeters for this section here. It needs a location, so I'm just going to set up a point. I'm going to set a point. I'm just going to click here on the Rhino window and for somewhere for it to start, and I'm going to set the size to 20. Alright, cool. So that's our radius of gyration, but to make it a bit clearer, I'm just going to put some text around that. So I'm going to concatenate. I'm just going to say Rx equals then the number and then space millimeters, and I'm going to add an additional input to that concatenate. Put that in there. That makes a bit more sense. And I'm just going to hide this point. It's a bit annoying. Now I've realized I did something, I skipped ahead a bit too far there. So you probably noticed that all of the values that come out of this calculation have three components, which is X, Y, and Z, which is what you want. So it's not really correct to just put all of them straight into this rounding up component. And you might think, how can I separate these X, Y, and Z components out? Well, that brace formulation can be split up with a vector component. So if I deconstruct vector, what I really want is the Rx. So I just want the X only. So it's actually 95 millimeters. So that's actually correct. Skipping ahead too quickly there. All right, so that's one property. I also want the second moment of area, or the Ix of the section. So I'm going to copy this. I need to deconstruct this as well. I'll put that into there. I'm going to call this Ix. Now this is going to be different for people in different countries, but in Australia we express the second moment of area in terms of millimeters to the power of 4, and it's usually in all our tables written by 10 to the 6 because it's such a large number. I know in the UK they use centimeters to the 4th power, which also makes sense to me, but for this purpose of this demonstration I'm just going to do the Australian method. So I know that it's going to be a number which is by 10 to the 6 millimeters to 4. And to get that number, that's a raw number at the moment. To get it in the right decimal places, I need to divide it by 1,000, a million. So I'm going to just use a function for that. I only need one input. And this is where I can use this funny little format command. I'm not going to go into a lot of detail to this. It's easy to look it up online if you want more explanation, but I'm going to use this format just to tell it how many zeros I want to display. And the output is going to be the input, which is x, divided by 1 with 6 zeros. And my input is as before. Now I've overlapped the text there, so I'm just going to move that origin point up by 30 millimeters. Okay, so now we've got IX and RX. Turn that point off. So we've got information we can use to calculate deflection of the section, but what about the strength? So for that I'm going to need the section modulus, and I'm just going to do the elastic section modulus. So as all engineers, structural engineers will know, you normally, depending on the code, use a effective section modulus, which you can pull out of tables or look at the code to calculate, and it gets a little bit complicated, but for a very basic idea of what the value is, I'm just going to show you the elastic section modulus, which is something you learn at uni, and is easy to calculate for this purpose. You can obviously modify this script to make it as complicated as you want though. So to get the elastic section modulus, I need to do a little bit of calculation. I need to work out, I'm just going to use I over y, where the y is the distance from the centroid to the most extreme fibre of this section, extreme point of this section. Okay, to do this, I'm going to first get all the points that make up this section. For that, I'm going to use this control points component. So that's going to give me all the points of this shape. Now I need to find the furthest one from this centroid. So there's a lot of ways of doing this, but the way I'm going to do it here, and I'm just looking at X as well, so to make it simple, I'm going to split this point up into its X, Y, Z components, all of these points, so it's given me 11 points there. I'm just going to sort the Z values, the Y values. So that's ordered from 0 to 246. I'm going to reverse that because I want the highest number. And then just in set, I'm just going to get the first value, which is now the highest number. That's item 0, 246. Then I'm going to subtract that from the centroid Y value. So if I go to vector, deconstruct point, I find my centroid, which is here. So that's giving me a y value, and I'm just going to subtract those two. The high y with the centroid y gives me 123. Now, because I can make L's in any sort of shape, I've now calculated this top fibre, the topmost point of this section, to the centroid. But if the centroid isn't equal, as far as geometry goes, it could also be the bottommost point to the centroid. So I need to test which of those two is the worst case. So here I'm going to, I know this is 0, which is easy. So I know that this distance is just the y value of that minus 0. So in other words, it's just the y value. So I'm just going to use the sort function again. And I'm going to take the y value, as I said, and the other y value, which I calculated. I'm just going to flatten both of these. So for a C, they're both going to be the same, obviously, but for an L, they're going to be different. And then I want the highest of those. So again, I'm going to reverse that and take the first value, which will be the highest. So I'm just going to use the simple formula for elastic section modulus, which is I over y. We've now got what we need. So it's just a division. The I, which I had before, divided by the y, which you've calculated, and that gives us elastic section modulus. Now if I want to display that on the screen as well, I'm just going to copy this display part. My vector, I'm going to change this number to 60 because it's another row up. This is going to be my ZX. Now, this is specific to Australia. I know in America they use SX for section modulus, but this is an Australian example, so we call it Z here. And it's 10 by 10 to the 3 millimeters to the 3. So each country is going to do this differently, but anyway, I'm going to plug this number into here, and I only need to get rid of 3. It's 10 to the 3, so I only need to divide by 3, 1000. So that's giving me my elastic section modulus. So now we can control our section and get our properties straight out. So last thing I'm going to do is turn this into an I section. So to do that, we've already got our middle part, which is controlled by this, which is this rectangle here. So I'll preview that again so you can see it. So before it was moved, it was down starting at origin. So it's just a matter of easily moving not only the Y, which we've already done, but the X. And we just need to move it by half of the width of the top flange and half of the width of the rectangle itself. So I'm just going to use a function for that. We're going to take the width of the first section and the width of the second section. And it's simply going to be x over 2 minus y over 2. Oops. So I've turned that old rectangle off. Now I've got an eye, which we can control pretty easily. And it gives our properties straight away. Thanks for watching this structured parametrics video. Leave a like or subscribe if you found this useful, and we'll see you in the next one.